Cover section 15.7, which deals with maximum minimum values of functions of two variables. So let's first look at the definition. A function of two variables has a local maximum at the point AB if f of xy is less than or equal to f of AB when xy is near the point AB. This means that f of xy is less than or equal to f of AB for all points xy in some disk about the center AB. The number f of AB is called a local maximum value. If instead f of xy is greater than or equal to f of AB, then we say AB is a local minimum value. Just to give you an idea, here I have a picture of a surface. It's a paraboloid is what it is. And if you notice, if we look at this function and we think of it as z is equal to f of xy, at this point right here, I have the lowest z value. And therefore, and I'm showing at that point, the point 1, 3 is the point that gives us that point on the surface, the point 1, 3 in the xy plane. If I take z of f of 1, 3, that z coordinate is the absolute lowest, and therefore we say that at the point 1, 3, the function has a local minimum. And in fact, for this particular function, it's an absolute minimum because it's the absolute lowest z value for the entire graph. So today what we want to figure out is how can we get those points, just as when you took calculus 1, if you had a function that looks like this, we had a relative max here and a relative min here, and we wanted to find, where are those x values for which our function has its relative max and its relative min. Well, back in calculus 1, you might remember, those points at which you attained a relative max or a relative min, if you took the derivative, which was the slope of the tangent line, the derivative at those two values was equal to 0. And we're going to find something quite similar to that in functions of two variables. Well, in fact, let's look. If I take the point 1, 3, and what I did on Maple is I held y constant. So I just looked at the curve on the surface where f of xy, the curve z equals f of xy, where I kept y stuck at 3. All right, and I got this curve. And notice at that curve, on that curve, at the point 1, 3, if I take the partial derivative with respect to x, I get a horizontal tangent line, and therefore the partial of f with respect to x at the point 1, 3 is equal to 0. Then I went on Maple, and instead I held x constant, x equal to 1, and I looked at the curve on the surface z equals f of xy, where x is fixed at 1. And if I noticed, I got a curve very similar to what I get what we got in calculus 1, and the tangent line to that curve is also horizontal, so that the partial of f with respect to y at the point 1, 3 is also equal to 0. And if you might notice, if you go back and you look, you could say, gee, Mrs. Strocko, I could slice this curve any way I want. Maybe I want to slice it this way. And no matter how I slice it, in other words, and no matter which directional derivative that I look at, I am going to get a horizontal tangent. But first of all, our candidates for max mins are going to be those for which the partial of f with respect to x is 0, and the partial of f with respect to y is equal to 0. All right, so we have a nice little theorem here, which is going to summarize that. It says if f has a local max or a min at the point AB, and its first order partial derivative of f, the first partial derivatives of f exist, then the partial of f with respect to x must equal 0, and the partial of f with respect to y must be equal to 0. So in other words, if we have a function z equals f of xy, and we want to find those values for which the function is attaining a local max or a local min, our candidates are going to be those points for which the partial of f with respect to x is 0, and the partial of f with respect to y is 0. Now, just as when you took calculus 1, you might remember we had a function that looked like this. And notice right here at this point, the slope of the tangent line was equal to 0. F prime was equal to 0 at that point, but it was not a max and it was not a min. All right? So could that happen in two-dimensional calculus? Well, absolutely. Let's look at the old saddle. Okay, here's the function that you might remember z equals f of xy is a saddle. Now notice if I slice it with y held constant, or in fact here I'm slicing it with y equal to a constant, my curve is concave down. Okay, and if I slice it with x equal to a constant, my curve is concave up. And for both of them, the slope of the tangent line, here we held y constant, so we have the partial of f with respect to x is 0. And here we held y constant, x constant, so the partial of f with respect to y is 0. But I guess you all would agree that this point is not a max and it's not a min, because if I look at a little neighborhood about that point, there's points that have z's lower than it, and there's points that have z's higher than it. So we call that a saddle point. And notice the partial of f with respect to x and the partial of f with respect to y, both are equal to 0. So the question is, how can we tell if we find those points for which the partial of f with respect to x and the partial of f with respect to y is equal to 0, how can we tell that we have a saddle point, or how can we tell that we have a max or a min? Well, the key is the following. If you notice, if I have a paraboloid, okay, here's a paraboloid. Notice, no matter how I slice it, I'm always going to get a curve for which the partial of f with respect to x, the directional derivative is going to be equal to 0, no matter how I slice it. In particular, the partial of f with respect to x and the partial of f with respect to y, both are equal to 0. But we have to know no matter how we slice it, we will get the partials to be that way. And also, we need to have all of the concavities to be the same. Like if you have a minimum, you're going to be concave up all the time, or if it's a max, you're going to be concave down. So we have what's called the second derivative test, and we're not going to prove this. I'm just going to give it to you. Your book does give you some semblance of a proof. But what it says is this, the second derivative test. Suppose you have a function z equals f of xy, and it has continuous second partial derivatives on some disk around some point AB, all right? And at this point AB, the partial with respect to x is 0, and the partial with respect to y is 0. So we know that AB is a candidate for being a local max or a local min for this function z equals f of xy. What we need to do next is evaluate what is called the discriminant. I represent it with a capital D. Now here I have it written with the fancy partial with respect to x in this form, but another way to write it would be you're taking the partial of f with respect to x times the partial of f with respect to y with respect to y. So it's the second partial with respect to x times the second partial with respect to y minus, and then you'll take the partial with respect to x with respect to y squared. And that is called the discriminant. Now what this second derivative test says for function of two variables, it says if d is greater than 0, then your function is a candidate for being a max or a min. Now going back here, notice saying if d is, these two are saying yes, you're a candidate for being a max or a min. What says slice it just in the x direction. When the discriminant is positive, it means no matter how you slice it, all of your slices will be concave up or concave down. So it says look at one slice. Look at the partial with respect to x, the second partial with respect to x. You might remember in Calculus 1, if you had a function that was concave up, its second derivative was positive. This is the same thing. If your second derivative is positive, yes, you're concave up and you will have a local min. If your discriminant again is positive, you're a candidate for a local max or min. Look at your second derivative with respect to x. If it's negative, you'll be concave down and you will have a local max. If d is less than 0, you've got a saddle. When d is less than 0, it means that no matter how you slice it, there'll be some slices that will be concave up, some slices that will be concave down, and so you're not a max or a min. So in summary, to figure out your max and mins of functions of two variables, first solve this set of equations. Partial of f with respect to x, partial f with respect to y is equal to 0. All the points that make these two equations equal to 0 are your candidates. Then make your list of all your points. Make a list of all the points that make these two derivatives equal to 0. If the discriminant is greater than 0, you have a saddle, and you're done. If the discriminant is less than 0, then yes, you are a max or a min. Then what you need to do next is take the second derivative. Since you're a max or a min, evaluate the point at the second derivative. Now, we choose the second partial with respect to x. You could also choose the second partial with respect to y, because having the discriminant, I have this backwards, when the discriminant is less than 0, you are a saddle. When the discriminant is greater than 0, you have a max or a min. And when the discriminant is greater than 0, that says no matter how you sliced it, you would be concave up or concave down for all the slices. So if fxx is positive, then fyy will be also positive. But if xxx is positive, that means you're concave up and you have a min. And if fxx is negative, you are concave down and you will have a max. All right, so having the discriminant less than 0 tells you that you have a saddle. If the discriminant is greater than 0, you're a candidate for a max or a min, and you have to further check your second derivative. So let's do an example. Determine the local max and min values and saddle points of the function f of xy is equal to x to the fourth plus y to the fourth minus 4xy plus 1. So first of all, we have to solve the system of equations. The partial of f with respect to x is equal to 0, and the partial of f with respect to y is equal to 0. So let's see, if I take this and the partial of this with respect to x, I get 4x cubed, partial with respect to y is 0, minus partial of that with respect to x is 4y, and I need that to be equal to 0. If I take the partial of this with respect to y, I get 0 plus 4y cubed minus 4x is equal to 0. So I have a system of equations that I must solve. All right, so I'm going to play and solve it first, and let's see. First of all, why don't we, the top equation, divide through by 4, so I get x cubed minus y is equal to 0. And if I divide the bottom one by 4, I get y cubed minus x is equal to 0. So this top equation, I could say x cubed is equal to y. Okay, and if I use substitution, I can take this and plug it into the second equation. So where I see y, I can replace it with x cubed. So I have y cubed minus x is 0. So where I see y, I take it out, and I put in x cubed. And that gives me x to the 9th minus x is equal to 0. Okay, now how am I going to solve that? Well, I'm going to factor it. I can factor out an x. So we have two cases. Either this is 0, or x to the 8th minus 1 is 0. Well, if x to the 8th minus 1 is 0, x to the 8th is 1. And what numbers to the 8th power will give you 1? Plus or minus 1. All right. So let's make a list of our points. We have x equals 0, or we have x is 1, or we have x is minus 1. Okay, those are our values that we got. Now we have to get the y's that go with that. But remember, we had x cubed was equal to y, or y was equal to x cubed. So if y is 0 cubed, it'll be 0. Here when x is 1, y is going to be 1 cubed, which is 1. And here when x is negative 1 cubed is negative 1. So these are the 3 points that I need to check. These are my candidates for max and mins. They were the points that are the solutions to this system of equations. Okay, now what are we going to do? We're going to take these points and we're going to evaluate the discriminant for these points. Okay, so let's figure out what our discriminant is. Going back to our function, it's f of xy equals x to the 4th plus y to the 4th minus 4xy plus 1. A few minutes ago, we evaluated that fx was equal to 4x cubed minus 4y. Fy was equal to 4y cubed minus 4x. So fxx is going to be, we're taking the partial of this with respect to x, we're going to get 12x squared. And fyy is going to be the partial of this with respect to y, which is going to be 12y squared. And fxy is going to be taking the partial of this with respect to y, is a negative 4. So our discriminant, which is fxx times fyy minus quantity fxy squared, is going to be 12x squared times 12y squared minus a negative 4 squared, which looks like 12 times 12, 144 x squared y squared minus 16. Okay, that's what we got our discriminant to be. So coming back here, we are going to evaluate, okay, each of these points using this discriminant, okay, using that discriminant. So let's see. If I plug in 0, 0 into that discriminant, I get 144 times 0 minus 16. I get a negative 16. Okay? If I plug in 1, 1, I get 144 times 1. Oh, this is y squared, by the way. 144, 1 times 1 is 144 minus 16. 144 minus 16, if I just do it on the calculator, I know it's positive and that's all I care about, but 144 minus 16 is 128, which is positive. And plugging in a negative 1 again, we're getting 144 times 1 minus 16, which gives us 128. Okay, so when the discriminant is negative, we have a saddle. So we have a saddle point at 0, 0. But we also, here the discriminants are positive, so they are candidates for max mins. So we have to check, are we concave up or are we concave down? And we do that by checking the second derivative. In our textbook, they're choosing to use the second derivative with respect to x. You also could do the second derivative with respect to y and you'll get the same answer. Well, pulling this back a few minutes ago, we evaluated fxx for this function, and we got 12x squared. So if I plug in x equals 1 in here, I get 12, which is positive, which means I'm concave up. So I have a local min at the point 1, 1. And at negative 1, again, if I plug x equals negative 1 into 12x squared, I get 12 times a negative 1 squared, which is 12. So I'm concave up, and I have a min at negative 1. So this is a bit involved in terms of evaluating whether or not I have a max or a min, but it's quite simple. What did we do? We first found our candidates by setting the first derivatives equal to 0, and then we further investigated by evaluating the discriminant at each of those points that make both the first and derivatives with respect to 0, with respect to x and with respect to y equal to 0. If the discriminant was negative, that point was a saddle. If the discriminant was positive at that point, we further had to investigate the second derivative. If the second derivative was positive, we're concave up, just like we were in Calculus 1, and we have a local min. If that second derivative was negative, we would be concave down, and we would have a local max. Okay, let's look at this one now. We want to look at the function f of xy equal to e to the minus 4y minus x squared minus y squared. All right, so first of all, we're going to find our candidates for max mins. So we got to take the partial with respect to x. Now notice this function's in the form of e to the u. And when you take the derivative of a function of the form of e to the u, the derivative is e to the u, all right, times the derivative of the exponent. Now we're differentiating with respect to x, so derivative of 4y is 0, derivative of minus x squared is minus 2x, derivative of y squared is 0. So my partial with respect to x is minus 2x times e to the 4y minus x squared minus y squared. Okay, now I have to take the partial with respect to y. The partial with respect to y is going to be, again, e to the u times the derivative of u. Well, let's see. The derivative of 4y is 4. Derivative of minus x squared is 0. Derivative of minus y squared is minus 2y. So fy is equal to 4 minus 2y times e to the 4y minus x squared minus y squared. Okay. Now, what do we do next? We have to have the partial with respect to x, which is minus 2x e to the 4y minus x squared minus y squared to equal 0. And we also need the partial with respect to y, which is 4 minus 2y quantity, e to the 4y minus x squared minus y squared equal to 0. Okay? And you go, my goodness, how do I solve that? Well, this isn't that bad, and let's talk about why. Remember back from your calculus 2 days that e to any power is always positive. The graph of y equals e to the x looks like this. It never crosses the x-axis. It's never equal to 0. So if I have this times this is equal to 0, this can never be 0. E to any power is never 0. So the minus 2x must be 0, or x must be 0. Okay? And again, if I have this times this, since e to any power is always positive, divide by that on both sides. You get rid of it. We have 4 minus 2y is 0, or y must be 2. So we only have one point that we have to check, the point 0, 2. We have the point 0, 2 that we must check. All right, so we have to do the discriminant. Okay, so bringing this out, what do we have so far? Well, so far, we had the partial with respect to x was equal to minus 2x e to the 4y minus x squared minus y squared. So the partial with respect to x, the second partial with respect to x is going to equal. Now, unfortunately, this is a product. So we have to differentiate it. We've got to take the first times the derivative of the second. And the derivative of this is e to the u times u plus the second times the derivative of the first, which is a negative 2. So let's see. We have here fxx is equal to 4x squared e to the 4y minus x squared minus y squared minus 2 e to the 4y minus x squared minus y squared, which is a bit bloody. I think I'm going to factor out the e to the. So I get 4x squared minus 2 e to the 4y minus x squared minus y squared. Okay. Notice the only point we said we had to check was the point 0, 2. So since we're only checking the discriminant at the point 0, 2, why don't we evaluate fxx at the point 0, 2? We plug in the point 0, 2. If we put a 0 in for x here, we get 0 minus 2 is a negative 2. E to the, putting a 0 in for x, I get 0. 4 times 2 is 8, minus 2 squared is 4. I get a negative 2 e to the 4th. That's what my second partial is evaluated at the point 0, 2. Okay, now we got to find fyy. Okay, coming back. We had fy was equal to 4 minus 2y e to the 4y minus x squared minus y squared. Unfortunately, this is a product. So fyy, again, this is in the form of u times v. So we have to go the first times the derivative of the second. So it's going to be e to the u times the derivative of that with respect to y. So we're going to get, again, 4 minus 2y plus the first times the derivative of the second plus the second times the derivative of the first. The derivative of that with respect to y is a negative 2. So I have fyy is equal to 4 minus 2y squared e to the 4y minus x squared minus y squared minus 2 e to the 4y minus x squared minus y squared. And again, the only point we're interested is 0, 2. Let's evaluate my second derivative at the point 0, 2. So I'm putting a 2 in for y here. Well, 2 times 2 is 4. 4 minus 4 is 0. So this is 0. So I just get a negative 2 e to the 4 times 2 is 8 minus 0 minus 4. I again get a negative 2 e to the 4th. Okay. Lastly, we've got to do fxy. Well, I think I'm going to find it easier to start with the partial with respect to x. So if I want to get fxy, all right, again, this is a u times a v. So it's the first times the derivative of the second. That's going to be e to the 4y minus x squared minus y squared times, now we're differentiating that with respect to y, so we're going to get 4 minus 2y. And then we could say plus the second times the derivative of the first, but the partial of 2x with respect to y is just 0, so this part just drops out. So our fxy is equal to minus 2x times 4 minus 2y e to the 4y minus x squared minus y squared. So fxy evaluated at the point 0, 2, since we're putting a 0 in for x here, we get a negative 2 times 0 is 0. 0 times this is 0 times anything else is 0. The partial of f with respect to x with respect to y at 0, 2 is 0. So, for the point 0, 2, our discriminant, which is fxx times fyy minus fxy squared, is equal to, we got fxx evaluated at 0, 2 to be negative 2 e to the 4th. We got fyy evaluated at 0, 2 to be negative 2 e to the 4th. We got fxy at that point to be 0, so our discriminant is 4 e to the 8th, which is positive. So therefore, 0, 2 is a candidate for being a max or a min. But in addition, we did evaluate already the second derivative at 0, 2. We got it to be a negative 2 e to the 4th, which is negative. The discriminant positive is telling us that no matter how we cut it, all the cuts will be concave down or concave up. This cut is concave down, and therefore we have a max at 0, 2. Now I chose to do this one because if you notice, the derivative was really messy. So when the derivative is really messy, it's best just go ahead and plug the point in right away instead of finding that big expression for the discriminant. If it's not too messy, then just bring it along for the ride for the whole problem. Let's look at another one. Next one we want to look at. Determine the local, max, and minimum values and saddle points of the function f of xy equal to 1 plus xy times the quantity x plus y. Now what I'm going to do first of all is I'm just going to multiply this out. 1 times x is x, 1 times y is y. xy times x is x squared y, and xy times y is xy squared. They want me to get my maxes and my mins and my saddles, so we're going to take our partial with respect to x, which is 1 plus 2xy plus y squared, and we're going to take our partial with respect to y, which is 1 plus x squared plus 2xy. Now, first of all, we have to set the first partials with respect to x and with respect to y equal to 0. So I need 1 plus 2xy plus y squared to be 0, and 1 plus x squared plus 2xy to equal 0. Now, if you notice, I mean, this is a system, it's called a nonlinear system of equations. Solving for x in terms of y really would not make much sense. But notice, this top equation, if you solve for the 2xy on that top equation, I get 2xy is equal to minus 1 minus y squared. And the bottom equation, if I solve for 2xy, I get 2xy equals minus 1 minus x squared. So since both of these equal 2xy, we can set them equal to each other. And let's see, the minus 1's cancel, and we could multiply through by a negative. And if y squared equals x squared, then y is x, or y is minus x. We have those two possibilities. So y could be x, or y could be minus x. So first I'm going to say, well, let's let y be x and see what happens. Well, coming back, if we let y equal x, again, these two equations must be satisfied. So if I plug in x whenever I see y, I end up with, let's do it into the top equation, I get 1 plus, where I see y I'm going to put x, and I get 3x squared equals a negative 1. Well, we're dealing with real variables, and there is no real number that 3x squared is equal to a negative 1. X squared is always positive, so there's no solution. So that's not going to happen. But we also had the possibility that y could be minus x. So if I let y be minus x, again, on the top equation, wherever I see y, I'm going to put in minus x. Wherever I see y, I put in minus x. And I end up with 1 minus 2x squared plus x squared equals 0, or 1 minus x squared is 0, or 1 is x squared. So we could have x equal to 1 or x equal to minus 1. Now notice here, the stipulation was y was the opposite of x. So if y is the opposite of x, if x is 1, y is negative 1, or if x is negative 1, y is 1. So these are the 2 points that I must check. 1, negative 1, and negative 1, 1. Those are the 2 points that we're going to check. So we're going to make ourselves a little chart. My candidates for max-mins are the points 1, negative 1, and negative 1, 1. Those are the points that we want to check. So what do we need to do? Well, first of all, we have to find out what is the discriminant. What is the discriminant? So coming back, all right, recalling the discriminant, we need all the second partials. So coming back, I have fx equal to this, so fxx is equal to, if I take the partial of this with respect to x, I'm just going to get 2y. I also need fyy. Fyy is, take this and differentiate again with respect to y, so we'll get 2x. We also need fxy. Fxy, if I take fx and differentiate with respect to y, I'll get 2x plus 2y. So my big D, which is fxx times fyy minus quantity fxy squared, is going to equal 2y times 2x minus quantity 2x plus 2y squared. Well, we could take a minute to simplify this. This is going to equal 4xy minus, if you multiply that out, you're going to get 4x squared plus that times that is 4xy, and then you need to double it, is 8xy plus 4y squared, or we're going to get 4xy minus 8xy is minus 4xy, minus 4x squared minus 4y squared is what we got our discriminant to equal. Okay, all right, so now we need to plug in 1, negative 1 into that. All right, and if I plug in 1, negative 1 into that, let's see, we're going to get, I just want to check my work here. Yeah, that looks good. Okay. All right, we're plugging in 1, negative 1. We're going to have a negative 4, and 1 times a negative 1 is a negative 1, times a negative 4 is 4, minus, that's going to be 4, minus 4, and that gives me 4 minus 8, which is a negative 4. So since that is negative, I have a saddle. Okay. In addition, I need to evaluate my discriminant at negative 1, 1. Well, negative 1 times 1 is a negative 1, times a negative 4 is 4, minus negative 1 squared is 1, so that's going to be a minus 4. Negative 4 times 1 squared is minus 4, and again, I get a negative 4. When the discriminant is negative, I have a saddle. And therefore, we have a saddle at both my candidates for max-mins at 1, negative 1, and negative 1, 1. Okay? I thought it would be nice for us to look at and do one that has trigonometry in it, because a lot of times my students struggle with the trig. So let's look at this one, which looks like it's hard, but it's not all that hard. Again, we want to find our candidates for max-mins. We're going to take our partial with respect to x and our partial with respect to y. Partial with respect to x is just cosine y, and partial with respect to y is going to be x times the derivative of cosine y with respect to y is minus sine y. All right, now, the top equation, if I want to make cosine y equal to 0, just remember what the graph of cosine looks like. Starts out like here. Your quadrantal points are pi over 2, pi, 3 pi over 2, and 2 pi. It starts up here, it comes down, and it goes up. This is equal to 0 here and here. All right, so that happens at pi over 2, 3 pi over 2, 5 pi over 2. Why don't we just say k pi over 2, where k is any odd integer. Now remember, our candidates for max-mins must make this equal to 0, and it must make this equal to 0. So it's fixed. Y has to be k pi over 2, where k is odd. Now notice, fy is equal to minus x sine y. Well, at those values, what does sine look like? Sine starts here and goes up. And at all those values where cosine y is 0, sine y is 1 or negative 1. So to make this equal to 0, we've got to take odd multiples of pi over 2. But if we take odd multiples of pi over 2, this guy right here is 1 or negative 1. So the only way we can make this be to 0 is let x be 0. So if we want minus x sine y to be 0, when you take the sine of those kind of numbers, you're not going to be getting 0. So the only way we can do it is get x equal to 0. So our candidates are going to be the points 0, k pi over 2, where k is any odd integer. Now you might say, geez, how are we going to define the discriminant for all those points? Well, it's not all that bad. All we have to do is evaluate our discriminant. So we got to find our second partials. So coming back here, fxx, derivative of cosine y with respect to x is 0. Okay, how about fyy? fyy, partial of this with respect to y, well, derivative of cosine y is sine y, so we'll have minus x cosine y, because derivative of sine is cosine. And fxy is, we take the partial of x with respect to y, we're differentiating this with respect to y, we're going to get minus sine y. Notice fyx will give you the same thing. If you differentiated this with respect to x, you'd get minus sine y. So our big D is fxx fyy minus fxy quantity squared, 0 times minus sine minus x cosine. 0 times anything is 0, so why even bother writing that? Minus my fxy is minus sine y squared. My big D is minus sine squared y. And remember, these points that we're looking at, our points that we were looking at were 0, k pi over 2, where k is an odd integer. Remember, we just looked at the graph. This is the graph of sine. And if you evaluate the sine at an odd multiple of pi over 2, you're getting 1 or negative 1. So our discriminant is going to be a 1 or a negative 1 squared, or we're going to get a negative 1, which tells me that these are all saddle points. Because for all of them, if you're taking an odd multiple of pi over 2, the sine of pi over 2 is 1, the sine of 3 pi over 2 is negative 1, you're getting 1 or minus 1. If you square 1 or minus 1 and square it, you get a 1, and then hit it with a minus sign, you get a negative 1. So we have all saddle points for this particular function. Okay, the next one that I chose for us to look at is a lot of times the equation that you go to solve isn't so easy to solve. You know, paper and pencil doesn't seem to be doing the trick. So in this particular one, they're asking us to use a graphing device to find the critical points. Your critical points are your candidates, those that make your two first partials equal to 0. The critical points of f, they want us to do it to 3 decimals, and then they want us to classify these critical points and find the highest or lowest points on the graph. So first of all, as always, we've got to find our partials. So what's the partial with respect to x? If I differentiate this with respect to x, I get minus 10y minus 8x. Okay, and we need that to equal 0. And the partial with respect to y, take this with respect to y, we're going to get minus 10x That's 0 plus 3 minus 4y cubed. Okay, and we need that to equal 0 also. All right, now this system is not so nice. If I look at it, I go, how can I solve that? Well, I could take the top equation and solve for y in terms of x. So I get minus 10y equals 8x, or if I divide by a negative 10, I get 8 equals a negative 8 over 10x, y equals a negative 8/10 x, or how about a negative 4/5 x? So I have y is equal to a negative 4/5 x. So what I'm going to do is I'm going to take the second equation, and wherever I see y, I'm going to put in x, okay, because I have y equals a negative 4/5 x. So I'm going to have minus 10x plus 3 minus 4 times a negative 4/5 x cubed, and we need that to equal 0. Okay. Now, because what I did is where I saw y, I took it out. Y's right here. I took it out and I replaced it with negative 4/5 x cubed. Now, we need to solve this equation. It's a cubic. I could simplify this, but I don't see any reason to. Well, I guess I could. Yeah, let's simplify it just a little bit. We're going to have a negative 4 cubed times a negative 4. So we're going to have this, just simplifying this a little bit. A negative cubed is a negative times a negative would be a plus. We're going to have 4 cubed times another 4. So up top we have 4 raised to the 4th, which is 256. And I think 5 cubed is 125. Okay. Okay, now to solve this, while I have the calculator on, what I'm going to do is I'm going to graph y equals minus 10x plus 3 plus 256 over 125 x cubed. And I'm going to look at when does this equal 0? Well, a function equals 0 when it crosses the x-axis. So taking out my calculator, I'm going to go second y equals, all right, and I'm going to put in negative 10x plus 3 plus 256 divided by 125 times x to the 3rd power. Okay, and I'm going to graph that, and before I graph it, why don't we just go F2, which is zoom, and I'm going to hit zoom 6, which is the standard one. And if you have a TI-83, you can do the exact same thing. Okay, and we're going to look at this graph. All right, looking at that graph, okay, negative 10x, let's hit y equals, I'm going to just make sure, negative 10x, I just want to make sure I have these just right before I go do any more. Negative 10x plus 3 minus 4y cubed, and we had y is a negative 4/5 x, negative 4/5. Yeah, that looks good. Okay, I think we're just fine. All right. Now, coming back and look, probably hit this little cord here so I can see the screen. All right, let's get that one solution there. So I'm going to go, on my screen, we want to hit math, which is option F1, 2, 3, 4. Now I need to see it, which is option F5. Okay, hitting that. Notice option 2 is 0. And to get a 0, they want a lower bound. So they want you to give an x value to the left of where it's crossing the x-axis, which is right there. Okay, and then I want to get an upper bound, and it's giving me 1.506. 1.506, which I don't really like. X is 1.506. So let's go back and just check my work here, because I did this before and I didn't get the same answer. So let's go back and look. We're looking at fx is minus 10y minus 8x. Fy is minus 10x plus 3 minus 4y cubed. We solve for y in terms of x, and we got minus 10y equals 8x divided by a negative 10, and we got 4/5 x. Plugging that into this equation, we have minus 10x plus 3 minus 4. This is our y, which is a negative 4/5 x. That whole quantity is being cubed. So 4 cubed times 4 gave us 256, which is fine. 5 cubed is 125 times x cubed. That looks good. Okay, so we wanted to put in a negative 10x plus 3 plus 256 over 125 x cubed. Let's see if I entered y right. Let's go back here and look at how I entered y. Oh, I left out an x. There you go. So I apologize. Those of you that were watching were going, Miss Strocko, you left out an x here. Coming back over here, I need an x right there. Okay, so I have a negative 10x plus 3 plus 256 over 125 x cubed. Much better. Now let's look at the graph. Okay. Notice there are 3 solutions. So we're going to find what those are. All right? And so we're solving for x. And they want us to get it to 3 decimals. So I'm going to go second, all right, not second, I'm going to hit F5 on this calculator, which is math. And option 2 is 0, all right. And it says to go lower bound. So I'm going to bring it along over here. All right, I hit enter. Upper bound, I want an x coordinate a little bit to the right. And it's telling me my first x value is a negative 2.347. Okay, now if I go F5 and hit 2 for 0 and move it along. Now again, we want a lower bound is an x coordinate to the left, and then we want an x coordinate to the right. And for that one, it's telling me a 1.3058. So that'll be 1.306. 1.306. Okay. Or is that just XC colon? All right. Help me, that's a point. All right, and then the last one, if we go F5 and then hit number 2, bringing that along here, we need a lower bound and an upper bound. And that looks like it's 2.4085. So how about 2.041? Now, since we have here, let's go back here, y is equal to negative 4/5 times x, all we have to do is plug these values in here to find out what y is. And I already did that to save us some time. So when I have a negative 2.347, we'll get like a 1. I just want 88. I really need an extra digit there. If I plug in 0.306, I get a negative 0.245. And if I plug in 2.041, I get a negative 1.63. Now we have to find out, are these maxes or are these mins? So what we have to do next is get the discriminant. Okay, so taking out our trusty paper, we have to get the discriminant. That's not too bad. fxx times fyy minus fxy squared. You're probably going to get a little daring like me and just write it all out at one time. Your fxx here is going to be, the derivative of that with respect to x is a negative 8. fyy, the derivative of that with respect to y is going to be a negative 12y squared. Minus, if I go fxy, if you take the partial of this with respect to y, you're going to get a negative 10. So my discriminant is going to be a negative 8 times a negative 12 is a 96y squared minus 100. All right, that's all my discriminant is. So coming back to my points, okay, if I plug these in, if you plugged in a negative 2 here, oh here, 1.88, and square it, you're going to get something bigger than 100. Minus 100, this is going to be positive for the negative 2037. If you plugged in 0.306, think about it. 0.3 squared is 0.09. So this is going to be 0.09 times 100. It's going to be like 9 minus 100. This is going to be negative. I just want to save us some time. And if I plugged in the 2.0, 2 squared is 4 times 96, definitely bigger. This is 100. So right now, I know I have a saddle here because that is negative. we've got to go back now and check fxx to see if we have a max or a min. Well, let's see. Coming back here, fxx was right here. It was a -8. So we have nothing to plug in here. fxx is a -8 because there's nothing to plug it in. So we're concave down at both spots, and so both of these points are going to be local maxes. Okay, we did enough of that. Remember, let's just talk for a second. Remember back in Calc 1, you had a function and you found your relative maxes and mins over the entire real numbers. And then there were times when we would just look at a limited domain. Maybe I just want to look at this. This point right here is not an absolute max because, if I look over the whole reals, because this function goes forever up. But if I truncate it at that, just looking at the red part of the graph, that is an absolute max. So when you limit your domain and you're looking at a continuous function, you could be attaining your maxes and your mins at your endpoints. So remember, we would find out those values for which this derivative is equal to 0. Those were your candidates. But then you also evaluated your function at the endpoints. We're going to do something very similar to that for two-dimensional functions. First of all, a closed set in R2 is a set that contains its boundary. So if I have a set like this in two-dimensional space, and I have the interior, to make it be a closed set, I have to include the edge. A bounded set is one that can be contained within some disk, or you could say within some square or some box. It doesn't go without bound. It's bounded. Okay, we have those two definitions. Now, extreme value theorem. If f is continuous on a closed bounded set D in R2, then f attains an absolute max and an absolute min at some point in that domain. So it says if you have a continuous function on a closed bounded set, it must attain a max and a min on that set, which is very nice. We're not proving that. That's an advanced calculus concept. Now, I copied this out of the book, and I think it's sort of much to do about nothing, but let's just read what they say, but then let's talk about what they're saying. To find absolute max and min values of a continuous function on a closed bounded set, find the values of f at the critical points of f in D, find the extreme values of f on the boundary of D. The largest of the values, it will be your absolute max. The smallest will be your absolute min. Now, what are they saying? Let's talk. Let's look at this one. Find the absolute max and minimum values of the function f of xy equals x squared minus 2xy plus 2y on the rectangle D, which is equal to all the points where x is between 0 and 3 and y is between 0 and 2. Let's draw what this domain looks like. X is going from 0 to 3, and y is going from 0 to 2. We are talking about all the points in here. This is a closed set because we're including the boundary, and it is bounded because, I can put a disk around it and enclose it. Now, we want to find out just on that rectangle, including its interior, what is the largest value of the function and what's the lowest value of the function. First of all, we're going to worry about what are my candidates for the points inside. For the candidates for the points inside, we're going to use the techniques that we've just developed. We're going to take our first derivatives, set them equal to 0, but we don't have to do the discriminant stuff. We don't have to do the discriminant stuff. All we're going to do is get our candidates for what's inside. So step 1 is set fx equal to 0, fy equal to 0, and solve that and get all those points. So taking those and setting them equal to 0, let's see what we got here. Fx is pretty easy. Partial of f with respect to x is 2x minus 2y. Partial with respect to y is minus 2x plus 2. Now, since both of these have to equal 0, okay, because I'm checking the interior, the bottom one I can solve quite quickly, and I get 2 is equal to 2x, or x is 1. Now, knowing x is 1, I can plug it back into the top equation, And let's see, if x is 1, 2 times 1 is 2, minus 2y is 0, or 2 equals 2y, or y is 1. Now let's check, is 1, 1 actually in that rectangle? Well, yeah, 1, 1's right here. So 1, 1 is a candidate. That's a point at which my partials with respect to x and my partial with respect to y both equal to 0. So we're going to list our candidates, the points that we need to check. We're checking the function f of xy equal to x squared minus 2xy plus 2y. And our first point that we want to check is 1, 1. Okay, and I'm going to just save that paper for later. Now, this is something different. We now have to check the border. Now, how are we going to check the border? First of all, let me say, at the edges where you have corners, you can always have a possibility that weird things could happen at the corners. So we're going to throw all the corners in as points to check. So this point right here is 0, 0. This point right here is 3, 0. This point is 3, 2. And this point right here is 0, 2. So we're going to throw all the corners in that we're going to check. So we're going to plug in, we're going to check 0, 0, 3, 0, 3, 2, and 0, 2. Okay? Now, will we get any others? Now, this is the part where students I tend to lose them. So now listen to me. We are going to use Calculus 1 techniques to go along the border and see if there's any extra points that we need to use. What we're going to do, now notice we have 4 sides that we have to check. We're going to change our function f of xy into a function of one variable. Now watch how I'm going to do this. First I'm going to check this border right along here. We'll call this side 1. Now to check side 1, what can you tell me about side 1? Every point on that side has y equal to 0. All right, so I'm going to go back up to f of xy. All right, and I'm going to plug in y equals 0 into that function. So I get f is equal to x squared minus 2 times x times 0 is 0, plus 2 times 0 is 0. So I get f is x squared. So along this border, f is just a function of x because y is always equal to 0. So to get any candidates using Calc 1, you say, oh, candidates for max-mins when you have a function of a single variable, take your derivative and set it equal to 0. Well, that would give me x equals 0. Well, we already have that point because on that border where x is 0 is right there, 0, 0, and I already threw it in. So I don't have any extra points. Now let's check border 2. Now for border 2, what can you tell me about border 2? Well, on that side, x is always equal to 3, right? Every point along that side has x equal to 3. So for border 2, since every point on that side has x equal to 3, we're going to come up here and we're going to plug a 3 in for x. So we're going to get f is equal to 3 squared is 9 minus 2 times 3 is 6y plus 2y, or f is 9 minus 4y. Well, notice if you take that derivative, now notice what we're saying is along that border, f is just really a function of y. So we say, can that f prime be equal to 0 ever? Well, no. F prime here is a negative 4. Can't set that equal to 0, so no extra points for border 2. Let's try border 3. And yes, I know this is tedious. On border 3, what do you know about all the points on that border? Oh, the the y coordinate is 2, isn't it? Along that whole border, your height is 2. So for border 3, y is 2. So wherever I see y, I put in 2. So 2x times 2 is 4x, plus 2 times 2 is 4. Now notice this one, if I take f prime and set it equal to 0, I get x is 2. Now notice on that border, when x is 2, y is 2. So we have another point right here, 2, 2, right there on the border that we have to check. So I'm going to add that to my list of points that I need to check. If you were daydreaming, let's go back and look. What I did was, for that top border, I plugged in y equals 2. I plugged in y equals 2 into the function. I got this, took the derivative, And when I set the derivative equal to 0, I got x is 2. On that border, y is 2, so we're going to check the point 2, 2. Lastly, we have to check the fourth border, and that fourth border, I think all of us would agree, has x equal to 0. So for border 4, if I plug in x equals 0, my function becomes 0 minus 0 plus 2y. If you take f prime, you get 2. That can't be equal to 0, so we get no extra points. Now coming back here, we have all of these 6 points check. 1, 1, 0, 0, 3, 0, 3, 2, 0, 2, and 2, 2. And what we have to do is evaluate f at all of those points. Okay, now I'm going to do it on the calculator. I'll show you how you can define a function on the calculator. The definition of the function is x squared minus 2xy plus 2y. So first I'll turn my calculator on. I'm going to hit F4, and option number 1 is define. No, I didn't want to do that. Turn my calculator on. We're going to go to F4. Did I want F4, 1, 2? Let me go back. Second home. Let me get to the home. I want to hit F4, which is other there. Excuse me. Let me hit F1, 8 just to clear this screen first to get rid of all this stuff. Now I'm going to hit F4. Option 1 is define. All right. Now I'm going to type f of x comma y, close parentheses, equals, and my function is x squared minus 2, no implicit multiplication, so we're going to type times x times y plus 2 times y, and hit enter. All right, now we want to evaluate f at 1, 1. So all I have to do now, since I've defined it as a function, is if I type f of 1 comma 1, I get 1. So f of 1, 1 is 1. F of 0, 0, I can do that in my head. That's going to be a 0. Okay, how about f of 3, 0? I would go f of 3 comma 0, and I get 9. So f of 3, 0 is 9. How about f of 3, 2? Well, if I backspace, f of 3, 2 is 1. How about f of 0, 2? Well, let's see. Backspace, I can put a 0 in here. F of 0, 2 is 4. And how about f of 2, 2? F of 2, 2, f of 2, 2 is 0. So coming back, putting the calculator away, and looking at all my functions, this one is the highest value, so I have a max at 3, 0. And this one and this one are the lowest, so I have a min at 0, 0 and 2, 2. Now the reason that I know I'm attaining a max or a min is that my continuous function with continuous partials is defined on a closed bounded set. And when you're defined on a closed bounded set, you know you are going to attain a max or a min. So first you find your candidates for max mins by setting fx equal to 0, fy equal to 0, and that gives you everything on the interior. But then you have to do the tedious job of going around the border. At any sharp corners, throw those points in for extra measure. Then, along each border, write your function as a function of just one variable, take the derivative, set it equal to 0. If anything pans out, those points you're going to want to check. And then all you do is evaluate your function at those points. Those are all your candidates for max mins. Since you know you have to attain a max or a min, the one that has the highest value is your max, and the ones or one that has your lowest value is your min. Let's just do a couple more just to make sure you're comfortable with this, because this particular topic students do struggle with. So let's look at this one. This is the function f of xy equals 3 plus xy minus x minus 2y. We are looking at the closed triangular region with vertices 1, 0, 5, 0, and 1, 4. 1, 4 is right here. And so we want to check this region that's bounded by all of that. So first, we want to see, are there any candidates in the interior of that region? To check to see if we have candidates in the interior, let's first copy our function so we have it. our function here is f is equal to 3 plus xy minus x minus 2y. Now, first of all, if you want to be on the safe side, you can say, oh, I always throw in the corners. So you're going to throw in 1, 0, 5, 0, and 1, 4. We'll throw those in first. Okay, those points we'll have to check. Let's put that aside for now. Put this aside for now. And let's get our candidates for the interior. For the interior, we set the partials with respect to x and partials with respect to y equal to 0. So fx here, partial with respect to x, is y minus 2. Okay, oh, excuse me, minus 1. Partial with respect to x here is 0. Partial of that with respect to x is y. Partial of that with respect to x is minus 1. Partial of that with respect to x is 0. So I get y minus 1 is 0. Partial with respect to y, that's going to be x minus 0 minus 2. Well, look how wonderful this is. If y minus 1 is 0, we get y is 1. If x minus 2 is 0, we get x is 2. So we have the point 2, 1. We should check that that is in the interior. And 2, 1 is right here. It definitely is in the interior. So we're going to add 2, 1 to our list of points to check. Now we have to check the borders. Now, how do we check the borders? Well, let's look. We have 3 borders to check. Let's take border 1. Can anybody give me an equation for border 1? Well, that's all the that's points on the x-axis. Points on the x-axis have y equal to 0. So what we do is we go back to the original equation. See, everything along here has y equal to 0. The equation of that line is y equal to 0. So I go back up here, and my f is going to be 3 plus x times 0 minus x minus 2 times 0. So my f is going to be 3 minus x. We are going to check as if I take the derivative of that and set it equal to 0, do I get any extra points? Well, if I take f prime here, I get a negative 1. You can't set that equal to 0. So we get no extra points because that derivative cannot be set equal to 0. Now we have to check border 2. This is border 2. I have to get the equation of that line. All right, that equation of the line is going to be y equals mx plus b. The slope when I go from here to here is I'm going down 4 over 4, so I can see my slope is a minus 1. And if I put in the point here, negative 1 plus what is going to give me 4, I can see it's going to be a 5. So, and let's check. If I put a minus 1 in here, 5 minus 1 gives me 4, and 5 minus 5 gives me 0. So the equation for that line right there is y equals minus x plus 5. So border 2, all the points on border 2 satisfy the equation y equals minus x plus 5. So what we're going to do is look at f, and wherever I see y, I'm going to put in minus x plus 5. Wherever I see y, I take it out and I put in minus x plus 5. So here f is 3 minus x squared. 5 times x is 5x minus x minus 2. Negative 2 times minus x is plus 2x. Minus 2 times 5 is minus 10. Okay, so if I simplify this a little bit, let's see. We have x squared right here, so we have a minus x squared. We have 5x minus x is 4x, and 2x is 6x. And we have 3 minus 2 is 1. Is that right? 3 minus 2 is 1. Minus 10 is minus 11. Okay. All right. And we're going to take f prime and set it equal to 0. Well, that is equal to 0 when 2x is 6 or when x is 3. Now remember, we're on the border where y is minus x plus 5. So y is minus 3 plus 5, which is 2. So we have the point 3, 2. Notice, coming back here, 3, 2 is right here. But we're going to add that to our list of points that we have to check. If I can find my list of points that I have to check. Let me find where I slipped it. Oh, here it is, right here. We have to check the point 3, 2. All right, now, We have border 3 yet to see if it will give us anything extra. Now border 3 is along here. That's a vertical line. All of them have an x-coordinate equal to 1. So for border 3, we're going to plug x equals 1 back into the function. And we have f is equal to 3 plus 1 times y minus 1 minus 2y. So we have f is 2 minus y. F prime is a negative 1, which can't equal to 0. So we get no extra points. So then we come back, and we have to plug these 5 points into f. Now I saved us some time and already did it. If you plug 1, 0 in, you're going to get 2. If you plug 5, 0 in, you're going to get negative 2. If you plug 1, 4 in, you're going to get negative 2. If you plug 2, 1 in, you're going to get 1. And if you plug 3, 2 in, you're going to get 2. So this function attains a max at my 2 highest values are 3, 2 and 1, 0. And that maximum value is 2. And it attains a min at 2 values, 1, 4 and 5, 0. Okay, let's look at one more. Next one I want to look at, and the last one that I'm going to look at, is the region we're evaluating. We want to get the max and the mins of this function over the region x is greater than or equal to 0, y greater than or equal to 0. So we're talking about the first quadrant here. And x squared plus y squared is less than or equal to 3. Now, I think you all realize that x squared plus y squared equals 3 is a circle of radius square root of 3. So our region looks like this. Okay. So first of all, we want to find out, are there any candidates in the interior? So what do we have to do to get our candidates? Our function is f of xy equals xy squared, and we're going to take our first derivative, see if we get any candidates. So fx is equal to y squared, and the partial with respect to y is equal to 2xy. Well, setting this equal to 0 says that y is equal to 0, and if y is 0, you can make this be 0 by letting x be anything, because 2x times 0. Okay, so our candidates are points x, 0. In other words, anything along this border. All right, so the first kind of points we want to check are the points x, 0. So since this whole border has the 2 partials equal to 0, we don't even have to check it because we've already included that whole border along there. Okay, because x could be anything. All right, now let's check our 2 borders. Now notice, this border along here has x squared plus y squared equal to 3. We'll call that border 2. Border 1 I didn't check because I'm throwing all of it in already. So for border 2, we have x squared plus y squared equals 3. And we want to write f, which is x squared, we want to write f, which is x y squared, as a function of one variable. Now normally I would tell you to solve for y in terms of x, but look here people, looking at this, y squared is 3 minus x. Along that whole border, since x squared plus y squared is 3, y squared is 3 minus x. So I can replace x with 3 minus x. So that border, I could write it as just a function of x squared, of just x, or as 3x minus x squared. Did everybody see how I did that? Because if I'm on this border, since x squared plus y squared is 3, y squared is always 3 minus x, just on this border. So where I see y squared, I replace it with, 3 minus x squared. I'm getting tired, so are you. So this is going to be x times 3, which is 3x, and x times x squared, which is x cubed. I apologize. Because we're replacing y squared with 3 minus x squared. So if I take this, now you see I'm rewriting this function just in terms of x. So if I have a max or a min just along that border, we would take our first derivative and set it equal to 0. And that's pretty easy to do. We get 3 equals 3x squared, or x squared is 1. And normally we would say x is 1 or x is minus 1, but we're not going to include x equals minus 1 because remember our region just has positive x's. And if x is 1, notice if you take x equals 1 and plug it back into x squared plus y squared equals 3, I get, let's see, x is 1, 1 plus y squared is 3, y squared's 2, or y is going to be square root of 2. Not plus or minus because we're in the first quadrant. So we're going to check the point 1 radical 2. So the next point that we're going to check is 1 radical 2. Okay. We have one more border to check, and that's going to be a pretty easy one to do. This one's along here. Along that border, x is 0, right? So if x is 0, notice you're going to get f is equal to 0 identically, huh? So I can't take the derivatives, but the derivatives are all equal to 0, so we'll include the whole darn border, which we'll write as 0 comma y. Okay. Now, we have, since, normally I say include the corners, but since we included this entire edge and this entire edge, we have included the corners. So we don't have to add the extra points, 0, 0. That point's going to be square root of 3 comma 0, and that's going to be 0 square root of 3. We're going to come back here and evaluate f at each of these points. Well, f evaluated at any point that's in the form of x comma 0 is going to be x times 0, which is 0. F evaluated here is going to be 1 times square root of 2 squared, which is 2. And if we evaluate f at 0, y, we get 0. So we get a min at the two sides. X equals 0 and y equals 0. And we get a max at the point 1 square root of 2, and that maximum value is 2. Now what you need to do is look over in your textbook, look over the examples on pages 989 to 997. Then I strongly urge for you to do numbers 1, 5, 7, 11, 13, 15, and 23 through 33, the odds. And I know I assign a lot of homework. I don't collect it. These are the problems I suggest that you do in preparing for your exam. Definitely you want to make sure that you do 2 or 3 of each kind in each section. If there are any that you struggle with, email me or leave me a voicemail message, and I can post the problems written out in a different form than you find in the Student Solutions Manual. Okay? I'll see you next time. Bye-bye.